last at the conference. Glad there's a couple of people left. Michaela gave you an overview of tests of general relativity that have been proposed with using gravitational wave measurements. And I'm going to pick up, I was able to actually drop out a whole bunch of slides. As I was watching Michaela's talk, I dropped out a few more. So hopefully I might even get to the end. But I'm going to talk about a couple of scenarios and then focus on one specific scenario, our recent work with Nico Yunus, Franz Pretorius, and one of my grad students, Laura Sampson, where we're actually looking at taking these parameterized PostEinsteinian waveforms and seeing how well Lisa would be able to measure some of the parameters in those waveforms. So the way I classify the kinds of tests you can do with gravitational wave astronomy are intrinsic and extrinsic. The intrinsic variety are basically various kinds of internal consistency tests. So looking at changes in, there are predictions in general relativity about the relationship between various multipole moments, the work by Ryan and following up Collins and Hughes with the bumpy black holes, where you're looking at, from one mode you figure out the mass and the spin, you check whether it matches with others, similarly with the black hole spectroscopy ideas. And so there's a lot, and this is far from an exhaustive list of these intrinsic tests that have been proposed. And I think those are very useful to have. It's nice to set those up as null tests. We can do the calculations in principle because they're within general relativity. So that's something that's seen a lot of attention. In the extrinsic tests, what you need is something outside of general relativity, so you need explicit alternative theory, and so people have looked at particular examples, heard about Brown-Sticky, massive gravitons, Chern-Simons, I don't think we've heard about that, but more recently, in an attempt to do something similar to the parameterized post-Newtonian approach for testing solar system dynamics and binary dynamics in general, looking towards that kind of framework for gravitational wave astronomy, Franz and Nico introducing the parameterized post-Einsteinian approach. So when you're actually trying to look at an alternative theory or think about what goes into making the gravitational waves, there's really, you can sort of break it up into three ingredients. One is the orbital motion, and that actually connects in with, say, a parameterized post-Newtonian. So the orbits the masses are on, that gives you a different time-changing multipole moments. You can worry about whether there's any kind of matter pollution around that you might mistake for a departure from general relativity, but it's just some mass in the vicinity that you hadn't thought about. But once you've got your orbital motion, then you get into the gravitational wave generation and different theories. The coupling to the different mass and current multipole moments can be different. They might carry different numbers of polarization states. So sort of the near-field conversion of the time-varying mass and energy flows and how that actually gets converted into a propagating radiation, that can also be different in different theories. And then finally, the propagation itself out in the wave zone can be affected by things like graviton having a mass. So the kinds of tests you can imagine doing, there are some tests you can do even if you really know nothing, that is purely a data analysis type perspective. That was like Michaela's, I think, final slide, where you can just think up just basic sanity tests you can do with no theory at all about what's going on. Some examples would be things like jackknife tests, where essentially what you would do is you're assuming that general relativity is correct in terms of your waveforms and your analysis, and you take, say, the first 6 months of an in-spiral, and then the next 3 months, and the first 6 months was probing the weaker gravitational field, the next 3 months probing into the stronger, and just see if the parameters you get from those two analyses are consistent. So just breaking up the data into regions that correspond to different levels of how relativistic things were. And also another thing, and I'll show a slide on this, if your theory, if your templates are not, if your model for the gravitational waves is incorrect, you're going to leave behind coherent residuals, and you can actually notice that there's coherent residuals in the data. So even without an explicit model, there are various data analysis tests that you can do. In terms of the parameterized tests, there was the work that Michaela already talked about, and I'll mention some, of modified post-Newtonian, where you take the post-Newtonian expansion but allow the coefficients to be arbitrary and see if you can measure them from the gravitational wave data and see if they recover the calculated values, and then the parameterized post-Einsteinian, which generalizes that idea further. So just to give you a basic idea here of how coherent residuals might work, suppose we didn't know about spinning black holes. Okay, we had general relativity, but somehow we just never thought about spin because we weren't that smart. But nature, of course, knows about spin, and here's a spinning in spiral, and you see some modulations from the spin, so around about a SNR of 700 or so in the in spiral. But suppose you had only thought to calculate templates for non-spinning black holes, and the best fit that you can get when you marginalize over all the different parameters actually gets you a pretty good detection. In terms of a fitting factor, you recover 90.96 of the SNR, but then that still leaves behind, in the case of Lisa, a coherent residual with an SNR of 218, and if this was an SNR squared, this would be a linear addition, it's just we do square roots.
What's the
and
spin here?
Sorry?
What's the spin?
I actually can't remember. I think it was sort of medium, sort of like mid-range. I think it was sort of like 0.5, 0.3 type.
It's big enough for this
right
test to make sense.
Yes. And then actually, if you went in again, and we've done this explicitly, sometimes by accident in the mock Lisa data challenges, you go back in and you run again with a non-spinning template, and you detect this residual now at around about an SNR of 180, and then you kind of keep on going, and it takes you like 10 non-spinning black hole templates to fully resolve a spinning one, and that gives you a sense that maybe something isn't working right. So that'd just be one. So you probably would have figured out if it was like some serious departure from GR, you would have noticed it just from without even really thinking. And these fitting factors, these ratios between detected and true SNRs, just run through some examples using slightly more clever techniques. Imagine that we could actually pick up some kind of coherent residual at an SNR of 10, but if the actual signal to noise is around 1,000, that means that you'd be sensitive to fitting factors that are equivalent to probing part in 10 to the 5 departures from GR, which is the same reason that we measure masses to sort of parts in 10 to the 5. So the sort of things these tell you, if you want to do tests of general relativity with Lisa, you need your templates to be that good to begin with, otherwise you're going to mistake a departure from general relativity from just a modeling error, right? So you have to get your modeling errors down low enough so that we can actually exploit this full potential here. As Michaela already mentioned, you've got to watch out for covariances between source parameters and the departures from GR that you're looking for, and I'll show some explicit examples where that happens. And of course, if you saw some departure with one system, you might think something maybe is funny, but if you start seeing it, if you have like 20 black hole detections with Lisa, and they all show a departure, then the evidence just continues to grow until you really feel like you need to look at alternative theories. In the history of using parameterized models, so the parameterized post-Newtonian, parameterized post-Keplerian has been a very valuable technique. Here's an example of the parameterized post-Keplerian getting applied to the golden pulsar. These are very nice ways of looking for departures from GR when you don't have a lot of good candidate models outside of GR. And up until very recently, we didn't have an example in general relativity, for gravitational waves that followed into this parameterized model, and I actually wrote a NASA proposal proposing to do that, and I got funded, and then Nico and Franz published a paper shortly after I was funded, and doing just that. So now I've kind of just teamed up with them and look at the implications, and we can look to further develop it. But it was a good idea. I was a little slow in getting it done. So prior to that, part of the motivation for the scheme that I was thinking of were the modified post-Newtonian waveforms. So you take a standard stationary phase approximation in general relativity has this form, if you're just looking at the leading harmonic, and then the phase, we've already seen this formula. And these numbers have been laboriously calculated out now to quite high order, but rather than using the calculations that have been done, you could use the observations to actually try and measure these parameters. So you can then treat these as free parameters and see how well a Lisa observation could recover the post-Newtonian coefficients in this expansion. And here is from the paper of Arun et al. Showing the fractional error in the the post-Newtonian prediction to how well you would recover it. So sort of fractional errors in the recovery. Obviously, you recover the leading coefficient the best, and then less so with the others. They actually varied all of the parameters simultaneously, and they used a Fisher matrix analysis, and in their paper they talked about the incredible degree of instability in their Fisher matrices, how horribly ill-conditioned they were.
Random numbers.
And I think it might have been a random number generator because I just don't, I don't see the results being...
There is one more thing hidden here. Basically, they chose a specific post-Newtonian model, but uncertainty between post-Newtonian models actually much bigger than what error that you get.
Yeah, but I think in this framework where you're treating it as a, if you look at this as just a, you've now just motivated this form for an expansion from post-Newtonian. They all have that form with different coefficient, so I think it's okay as a motivator for an alternative.
Yeah, but the numbers, actual numbers...
Will depend on the specifics, yeah. But anyway, if we moving to the parameterized post-Einsteinian form, which again Michaela's already shown, you get amplitude and phase corrections here. And here's an example of, there's a whole lot of different terms for in-spiral, merger, all these different parameterized post-Einsteinian coefficients, what they are in general relativity, what they are in Brand-Sticky, Chern-Simon, massive graviton, not known in here. You recover this modified post-Newtonian technique of Arun et al. If k is an integer, so whenever it resonates with the GR values. Here is what one of these waveforms looks like for a Redshift 1 in-spiral and merger and ring down of of this system here, 3 by 10 to the 6 on a 10 to the 6 is equals 1. It won't really probably be anything like this bright, but just to show you the waveform. Now, what I'm going to tell you about is rather than using the full waveform, which has a signal to noise of 10,000, I'm just going to focus on the earlier part of the in-spiral and truncate things here. So I just want to focus on departures that are visible in the in-spiral. And I think one of the motivations for doing that is how well we model the GR stuff here in time for these analyses. Whether we can get that to the accuracy that we need is less certain, but we do have good control over the description of the waveforms here in GR. So let's just look at what we can do using the in-spiral part alone. So for the in-spiral waveforms, we actually slightly generalized here and went to allowing for the possibility of unequal mass ratios, so introduces two new parameters. The one thing I want you to focus on here is this parameter u, which is just the chirp mass times the frequency, which goes as the it's a measure of how relativistic things are. If you look at the binary, this binary pulsar, which Nico and Scott looked at as putting bounds on some of these parameters, that's down at the sort of 10 to the minus 9 level in terms of how relativistic it is. For a LISA supermassive black hole in spiral, you're going to be probing these quantities between, say, about 10 to the minus 5, 10 to the minus 2 for this parameter. I mentioned this one here, a LISA white dwarf binary actually goes back and more like a pulsar is priming, probing the less relativistic end. And so you can actually do interesting things with the white dwarf binaries for corrections that come with negative powers of these coefficients, whereas you want the more relativistic end for probing when these coefficients little a and b are positive. We'll see that in the graphs that follow. So the framework in which we are doing this analysis doesn't use Fisher matrices to avoid the random number generator effect. And we're using Bayesian inference, so we're using the standard techniques now, parameter estimation using Markov chain Monte Carlo techniques. We use local covariance estimates to help drive the jumps, parallel tempering to move things around. It's a very useful technique of differential evolution. Gives very nicely mixed chains to get the posterior distribution of all the parameters, and it is very nicely able to explore all the covariances. And then we can also look at model selection, asking is this general relativity versus is this an alternative, so compute Bayes factors, odds ratios, and for that we use the technique of thermodynamic integration. That's just for the folks in the room that do these sort of things, just to let them know what techniques we're using. So here's some results. The red line is the bound that Nico and Scott calculated using the existing binary pulsar results on the decay rate for the binary pulsar, actually the golden binary, not the Hulse-Taylor pulsar. And see, it wins for negative values of this A parameter because it's more sensitive, it's down in the more slow-moving regime, so it wins there, whereas the gravitational wave observations, and this is a single detection out at redshift 1, if you had, say, 10 detections at redshift 3, accumulates to about the same amount. And in terms of alternative theories here, right up against the axis here at A equals 1 is what you would have for Chern-Simons gravity. So for something like that, LISA provides a better bound by many orders of magnitude than the pulsar timing. You might be wondering about this feature here. Well, that's when A equals 0, and what happens there, when A equals 0, the term in the amplitude then just goes like 1 plus A divided by the luminosity distance. So you get a complete degeneracy as A goes towards 0 between this alpha coefficient and the luminosity distance. And you see this here. Here's the luminosity distance, the alpha coefficient for A of a 10,000th. Here's the GR measurement of the luminosity distance if you didn't have any departures here from any departure from general relativity. And we end up with this huge covariance, so you end up with a very large spread in the luminosity, and that spread actually goes to infinity.
What happens to the U?
Well, it's raised to the power 0. A is 0. Almost 0.
Small a goes to 0.
Yeah.
Okay.
Little a goes
okay,
to
sorry,
0.
Sorry, yeah.
Yeah. So, that's why there is basically an infinite correlation at little a of 0. Okay. Now on the phasing sector, which is the B, beta, and big B parameters, I'm just setting that to 0, which is the dependence on mass ratio. So here again we have the pulsar bound slashes through like this. So right across, and this is now phasing, and of course the gravitational waves are very sensitive to departures in phase. Again, we have a couple of funny spikes, which I'll describe. Just to mark where two theories would lie, Brand-Sticky lies here, massive graviton lies here. Actually, the particular system I just described would not be constrained by this type of measurement, since for Brand-Sticky, two black holes actually don't give any departure from GR. Sensitivity parameters are the same, so they cancel. So it actually wouldn't, this particular system wouldn't be probing Brand-Sticky, but just to show where it lies in the graph. And what we have here, we have a spike here, and these happen for similar reasons as the last spikes we saw. And this helps explain why. If I take the results from Arun et al., which reduce to the parameterized post-Einsteinian tests when you stick with these fractional powers of B, like minus 5/3 here being the leading term, and then the other powers. That's what their paper would calculate for this system, and they're actually different from our calculations by 2 orders of magnitude. And I haven't had a chance to explore that further, why we differ by 2 orders of magnitude, but I'm just going to rerun their analysis using the Bayesian techniques next week, so I'll see what's going on here.
I mean, they are changing all of them, aren't they? So.
Yeah, but I'll be doing that too. There's really, the covariances between those terms are not that large, so I'm surprised by the fact. I would expect with allowing them all to vary, it would move up some. I don't expect it to move up as much. So I need to explore that further, but I don't know yet whether I'll find the same result or not. But it just seems like it's more of a boost than I would have imagined it to be from just the covariances. What happened here was that we're at a B value of minus 5/3, which corresponds to one of the terms in the post-Newtonian expansion. And so it becomes degenerate to a large extent with the chirp mass, because that's what the coefficient involves in GR for that leading term. It's not a perfect degeneracy now, because the chirp mass is also encoded in the overall amplitude, and it's also encoded in some of the higher post-Newtonian terms. So it's not 100% covariance like we had with the distance and the alpha parameter for A equals 0. But you see, it does make a big difference. The little blue blob there, that's how well the chirp mass would be measured in GR. And then this term here means that you end up with this large covariance. One of the things this also tells you that if you want to explore these things, you need to have really good techniques for mapping out the posteriors, because this is a very high correlation that you need to be able to move your Markov chains along and things, and that's challenging. You can see it works quite well, the techniques we're using to do this. The other parameter correlation is kind of fun. This one happens when B equals 0, and there's in the limit that little b goes to 0, you get 100% correlation between the parameterized post-Einsteinian parameter beta and the phase at coalescence. And here I've just chosen a value of b that's small but not yet 0, and this is wrapping around and around and around like a barber pole. So the uncertainty ellipsoid ends up wrapping an infinite number of times around when you, in the limit that b goes to 0. And again, to get Markov chains to walk up and down this likelihood surface is challenging, but again, the differential evolution is allowing them to do that. So that explains why you get these covariances. It just means that for those particular values, you just cannot, you just wouldn't be able to see a departure from GR. So I think finally, what I was showing you there, I didn't really explain what I was showing, how I derived those bounds. Those were sort of a poor man's bound, where what we did was we injected a general relativity waveform, and then we analyzed it using the parameterized post-Einsteinian waveforms and just looked at how big could, say, these coefficients, these amplitude coefficients alpha or beta be, and still, how well they would fit the data, seeing the sort of spread. And so that was taken off the variance in the alpha and beta parameters running on a pure GR waveform. So I'll try and say that one more time differently. If the universe really did use general relativity, and we did an analysis using parameterized post-Einsteinian waveforms, that's the kind of spread we would expect to see in our recovery of alpha and beta, okay, around 0. So that's sort of like a poor man's bound, just a cheap estimate. A more costly estimate is to actually do model comparison. So here what I did is I injected a source that happened to have these parameters. So it had a departure from general relativity. This B parameter was minus 0.5, and then beta, the amplitude of that term, then I just sort of dialed it up, and then I calculated the base factor, depending on what your prior odds are. This is proportional to the odds ratio between it being general relativity and some alternative theory. And you see that the odds that it's an alternative theory get quite large by the time you dial beta all the way up to 0.3. And if you compare that to the poor man's bound I showed in the last graph, that actually comes in around a factor of 10. So you'd really want to be a little bit higher up from those to, really be confident that you were seeing a departure. So those are sort of, you might want to boost those. That's sort of like a 1 sigma bound I was showing. You might want to boost it up to a 3 or a 4 sigma in a frequent assertive language. So the final thing is, what if you were analyzing general relativity waveforms, but it actually happened not to be general relativity. So this example again, and I analyzed it, and I'm worried about doing astrophysics, right? How much would it affect my astrophysical parameter recovery? And let's take beta of 0.3, where, you know, this kind of testing would suggest a very large departure from GR. How much would it bias? So now I have a non-GR waveform, but I use a GR template to recover it. How much does it bias the parameters? Well, here, for example, is how much it would bias the total mass estimate. Look how many decimal places. It's not much. So for astrophysicists, most of this stuff doesn't really matter. So again, that goes to the point that, you know, Lisa's able to measure these masses to these ridiculous levels, parts in, you know, total masses to parts in 10 to the minus 4, 10 to the minus 5, that sort of thing. And that's at the level that we start to probe departures from GR. But this is even like a stonking rate departure from GR. It's Bayes factors of 10 to the 12, and it still doesn't change the astrophysical interpretation of this source at all, basically. So it isn't necessarily a big danger for astrophysics. There might be particular examples where it does cause a problem, but you know, the examples I've looked at so far, I haven't really seen any big biases that matter. So this is something that's, I think there's a decoupling between the degree to which we want waveforms very accurately. The requirements from testing GR are just a whole different world from the accuracy you need waveforms for doing astrophysics. Okay, thank you.
It seems that if we were lucky enough to have two enemies from the same source, we could actually see how it increased its mass by eating the first star.
Yes.
Yep.
Yes, that's right, you could.
Questions?
I have a comment. It's actually related also to Michele's talk. People mentioning massive graviton, but only from the point of view of speed of propagation. But if you try to build a relativistic theory, I mean, it has much more consequences, like consequences on black hole, the horizon, and on the polarization state.
I guess the idea would be with a massive graviton, when you're looking at it as a, you know, a wavelength, that is so much larger than the near zone region, so you would maybe think that the near zone isn't really affected.
Well, because it's non-linear theory, I did have a look at something, and in particular, the combination of masses of gravitons, I found that there was no horizon. But redshift would be very so high that it would be.
It would look like a horizon in practice.
Mm-hmm.
Would the extra polarization states that you get as soon as you have a non-zero mass be detectable in any sense?
Well, the here is the most square of gravity.
Other questions?
Related to your last point here, I'm often asked when I give talks about Lisa and I talk about testing GR, people then say to me, well, if GR could be wrong, then how do you know Lisa's going to give us anything useful? And so I think, although you seemed slightly disappointed by this
I'm not disappointed
result,
by it.
I think this is really very important.
Yeah.
When we talk about testing GR, we also should clearly carve out the part of Lisa's expected observations that are pretty much independent of these.
Absolutely, and I think, you know, I haven't actually calculated it yet, but it's an interesting way of turning this around. It's, you know, if you look at for example, the bounds that we already have from the binary pulsar, and you take those numbers, you max them all out, then how much of a departure from the GR predictions for the waveform, you know, how of the parameters would it cause? And I just don't think in most cases it would be, you know,
very small because
yeah.
because we're only a factor of 10 in frequency for the binary pulsar below the Lisa values.
Yeah, so I think that we're pretty safe from having departures from GR mess up the astrophysics, and we can quantify that at least in this framework now. So we just haven't done that number, but yeah.
The other hand, I regret that I did not show my own work, but if you modeling uncertainty with those sensitivities, I mean, just the simple check we did with Kurt was to see if you use 3pn instead of 3.5, what biases in the parameters you get. And you get biases in the parameter that are way larger than the statistical error.
Yeah, but they're still small.
So, there's more for astrophysics, they're not as well as you can do here. So, but for us, the benchmark for astrophysics is masses to 10%.
Right, that's what I mean. Like
That-
all
that's-
these things are.
Sure, that we can do.
That's fine. That's fine. That's enough.
Factor of 2 is already like that.
100%.
Beyond that.
We'd have to artificially degrade it to be at 10%.
Yeah.
Then astronomers would love the mission.
Further questions?
Exactly.
Oh, GPS would have its own waves. Yeah.
Let's say need again.